Hi, my name is Henry Cook, and I work in the European HANA and Database Technology Centre of Excellence within SAP. I've worked in and around databases for many years, over 25, so the ACID properties of database are very old and very good friends of mine. And when I saw the request to author presentations on different topics, I was more than happy to spend a few minutes talking about them. Also, I thought it would be great fun to be able to say I've authored a corporate presentation entitled Henry Cook on ACID. So, ACID properties and transactions. SAP HANA is a fully ACID compliant database. Why is this so important? Well, as we'll see in a minute, the ACID properties are what enables you to be confident about the effect that your transactions are having on your database and the fact that you're maintaining the integrity of the database. The principles of how to handle transactions have been around for quite a while. In the 1970s, Jim Gray originated most of this thinking, and that was refined in a paper in 1983 by Andreas Reuter and Theo Harder, and it was they that coined the term ACID that we use today. The point here is that a lot of deep thought went into the ACID properties, and they've served the industry very well. Let's just remind ourselves of what a transaction is. It's typically a short period of piece of work requested by a user at an online terminal where a number of database actions, reads, update, inserts and deletes need to be done at the request of a user. These operations are all gathered together as a unit, and at the end of the transaction we expect all the work to have been done as we expected. Transactions come from the general concept of contracts. In effect, each transaction, like a legal transaction or a commercial transaction, is entering into a contract with the database, and the transaction expects the database to honour the work that it's being requested to do. The first ACID property is the transaction should be atomic. That is, it should be all or nothing. The transaction should either be carried out in its entirety, or it should be as if the transaction never existed, if the transaction couldn't complete. In particular, the database should not leave the database in a state where only part of the work has been done. So what this enables you to do is to be sure that the database at the end of your transaction is either in the state you intended or it exists as it was before you even touched it. We can see this in the language of transactions. At the end of the transaction, we ask for a commit. That is, we ask for a commitment from the database that it will have carried out all the work we've asked it to do. If it wasn't able to do this, we want it to tell us and then leave the database unchanged exactly in the state it found it. This is in day-to-day living. A good example of this is the marriage ceremony. That's a social contract where there's a transaction with two people, and at the end of that transaction, those people are either married or they're both still single. We can't come out of that transaction with one person still single and one person married. Now, it's possible for transactions to be atomic, to be executed in their entirety, but to make the database inconsistent. And the ACID property of consistency states that what the database should do is enforce the fact that transactions can only update the database and move it from one consistent state to another. Okay, so in what ways might we make the database inconsistent? Well, for example, if we have an inventory record, it should never be the case that inventory is less than 0. The demand for the inventory may be greater than the number of objects we have, but if we are recording the number of objects that are sitting on shelves, we should not be able to have minus 100 sausages. So outside of the world of Star Trek and antimatter, it should not be possible for us to have a negative amount of inventory. So if any transaction attempted to do that, we'd like to stop it. And the best place to do this is inside the database where it's centralized. Likewise, there may be some sanity checks we want to apply. If we're adding a customer record and we've worked out from their date of birth that they're 257 years old, we may begin to suspect that that record is inconsistent and would damage the integrity of our database. So we would want transaction manager, the database manager, to forbid that transaction. Equally, there are referential checks, what's called referential integrity, where if we're inserting order lines, we would want to make sure that there exists an order to put those order lines in. and so we'd like the database to enforce this as well. Now, the other way of doing this, if you didn't do this, you would have to rely on all the different programmers of the different transactions to actually do these consistent themselves. And leaving it to human beings pretty much guarantees an inconsistent result. Having it enforced in the database means that you're able to move the responsibility for that to a central point and police it in a central point. By the way, as an aside, sometimes you may not want to enforce referential integrity and be pragmatic about it, especially in analytical applications. You may want to mass load large tables in a particular order, and setting referential integrity can get in the way of that. So sometimes people put them in, sometimes they don't, but it's worth thinking about. For OLTP applications, it makes a lot of sense to have these rules, these business rules and integrity rules enforced within the database. And this also applies to all manner of rules, which can be constraints, cascades, triggers, etc., etc., etc. The third property that's proposed is isolation. Now, isolation doesn't mean getting lonely. After all, databases are made for sharing. But like any relationship, sometimes you need a bit of space. So in the relationship between the transaction and the database, it typically wants a bit of space from any other transaction that might want to come in the middle with the records that it's updating. So what isolation means is that the transactions will execute as if they are done one after another, serially. And it would seem to each one of the users that we can see drawn here that they've got the database completely to themselves. Now, in practice, they don't run serially, and under the surface, the database will do things with locking or some form of multi-version concurrency to hold up one of the transactions a wee bit, to let the other one complete, in order that each transaction sees a consistent view. Now, it's important to know that the isolation rule doesn't say anything about the order of the transactions. If we've got 3 transactions coming in at the same time, A, B, and C, and they all touch the same record, there's no stipulation about which order they should run in. But what the rule means is that those transactions will run as if they were in some serial order. It could be ABC, it could be CBA, it could be BAC, but each one will run so that the start of one transaction will take as its beginning point the end of one of the others. So each one sees a consistent status of the database. It does its transaction, it leaves it in another state, and you can't intermingle them at all. Think of the implications of not doing this. Your transaction would change its behavior based on the activity of other users in the system. It would be like your database was haunted with supernatural powers swooping in and changing the meaning of what you're doing. Enforcing isolation makes it possible to keep the changes distinct, and it's possible to have a clear audit trail and determine the responsibility for people who've made those changes. So finally, durability, the fourth of the ACID properties, states that if we've got these transactions and they're atomic, they're only moving the database from one consistent state to another, we've isolated users from each other so they can't interfere with each other. So we've got all these transactions making changes, and it would be kind of nice if when we logged on tomorrow, the results of our transactions, our changes were still there, and the next day, and the next day. In fact, there shouldn't be any further changes to the database unless we explicitly make them using other transactions. We want the changes that we've made to persist and to be permanent within the database. Now, it may well be that after we've made the changes, just a split second later, somebody may unplug the power to put in the coffee maker or whatever. And we want, when the power is restored, we want the database to come back, and we want the database to be exactly where it was at the end of our transaction. We want to see the changes that we made still in there. We can extend this. This is all to do, by the way, with the area of logging and recovery and backups, making sure that any changes we make go safely to non-volatile storage, and SAP HANA does this. And we may want to extend this to the whole area of data recovery, disaster recovery, across multiple sites. So if a fire breaks out, or we've got a bad storm, or a flood happens, and we lose the data center, maybe it blows up or it burns down. What we'd like is to be able to extend this concept across to a second data center. So we fire up the secondary disaster recovery center and we discover our database in exactly the same form that we lose it. Now that's clearly a more difficult job, but it's a simple extension of the ACID properties. So they're the basic ideas of ACID. I hope you found that useful, and thank you very much for listening.